Same function. 4 views, words to table to graph to formula. A function isn't just a formula, it's a rule assigning each input exactly one output. Key rule: one input cannot map to 2 different outputs. Domain equals allowed inputs. Range equals outputs you actually get. Each representation reveals different information. A description in words can define a function, no formula needed. Tables shine with measured data or naturally tabulated rules. You can plot the table points to see the trend instantly. Graphs reveal shape, increasing, decreasing, leveling off, spikes, repeats. Formulas are exact and let you compute outputs instantly. Real life, words to data to graph to, sometimes a model formula. A function can be represented in 4 ways, each reveals different information. Which representation is best for each situation? Drop answers in comments. 2 problems, same data, 2 completely different predictions, because someone picked the wrong type of function. In the next 10 minutes, you'll learn the essential function toolbox that powers calculus. You'll also get a fast way to choose the right model on site. Welcome to Section 1.2, Mathematical Models and Essential Functions. We're building a catalog of function families: linear, polynomial, power, rational, trigonometric, exponential, and logarithmic. So when you see a real situation, you can pick a model quickly. A mathematical model is a mathematical description of a real-world situation. You start with a problem, choose a function to model it, and use the model to make predictions. Then compare those predictions to real data. If it's not good enough, you refine it. Modeling is a loop. One crucial warning: a model is not reality. It's an approximation meant to be useful. Models often work well inside the range you measured, and fail badly outside it. So always ask, what assumptions am I making, and how far can I trust this? Now we build the toolbox. Most real-world models are built from a small number of standard function types. If you recognize the type, you can predict behavior, growth, decay, oscillation, blow-ups, leveling off, without doing complicated math. First, linear functions. A linear function has the form y equals mx plus b. The key idea is constant rate of change. The slope m is the rate and b is the starting value. Example: a service charges $10 plus $2 per unit. If x is units, the cost is c of x equals 2x plus 10. The table climbs by 2 each step and the graph is a straight line. Next, polynomials. A polynomial is a sum of powers of x with coefficients. Polynomials are popular because they're smooth and flexible. By changing coefficients, you can bend the curve. But remember, polynomials are usually most reliable over the interval where you actually have data. Here's the danger: a polynomial can fit data well inside the observed range, and become ridiculous outside it. That's extrapolation risk. Trust it most where you actually measured points. Power functions look like x to the a. Change the exponent, change the shape. X squared curves up fast when a equals 1, it becomes a straight line. When a equals 1/2, square root rises quickly then levels off. When a equals -1, 1 over x blows up near 0 and flattens far away. A rational function is a ratio of polynomials. The big visual feature is blow-ups. If the denominator hits 0, the function can shoot toward infinity. That creates vertical asymptotes, values of x you can't cross. Trigonometric functions model repeating patterns. If something cycles, sound, tides, seasons, trig is a natural fit. The graph is a wave that repeats with a consistent period. If your data oscillates, don't force a line, use sine or cosine. Exponential functions model growth and decay when change is proportional to the current amount. Constant percent change. Doubling every hour is exponential growth. Halving every hour is exponential decay. Exponentials change slowly at first, then very fast. Logarithmic functions are inverses of exponential functions. If exponentials grow fast, logs grow slowly. Logs are useful when growth slows down, or when you need to undo an exponential relationship. Here's your fast model picker. Constant rate, linear, smooth flexible fit, polynomial. Scaling laws, power or root. Denominator creates blowups, rational. Repeating cycles, trig. Constant percent change, exponential. Undo exponentials or describe slow growth, logarithmic. If you can classify the type, you can predict behavior instantly. Recap. Section 1.2 gives you the essential function toolbox for modeling. The goal isn't memorizing names, it's recognizing shapes and choosing the right model. Challenge. Rent increases by $50 each month. What model is that? And bacteria doubles every hour. What model is that?
Same function. New graph. One move. Shift it up. Add a constant outside. Stretch it. Multiply outside. Reflect it. Then combine moves. Outside changes go up and down. Add C outside. The graph shifts up. Subtract C outside. The graph shifts down. Inside changes shift left and right. Inside changes feel backwards. X minus 3 moves the graph to the right. X plus 3 moves the graph to the left. Outside multiplies change height. Inside multiplies change width. Multiply outside to stretch taller. Multiply by a fraction outside to shrink. Multiply inside to squeeze. Divide inside to widen. Negative outside flips over the x-axis. Negative inside flips over the y-axis. 1 base graph, 5 quick transformations, down, right, flip, stretch, and mirror. To add functions, you add their outputs. Watch the yellow point. It's f of x plus g of x at each x. When you add or subtract functions, x must be in both domains. The overlap is the only safe region. Products are usually fine, but quotients break wherever the denominator becomes 0. That x is forbidden. Composition means feed the output of g into f. First compute g of x, then plug that into f. Even with the same two steps, switching the order can change the result. So f composed with g is not the same as g composed with f. For composition, x only works if g of x lands inside the domain of f. So you have to check both stages. To understand a complicated function, break it into steps from the inside out. Here, add 9, then cosine, then square.
Your calculator can lie. A bad window or bad sampling can make it draw things that aren't real. Let's spot the warning signs and learn how to fix them. First we set a sensible window. Then we zoom to test what we see. And only then do we trust the picture. A graph only shows what fits inside the window. X from A to B, and Y from C to D. Change the window, change the story. If you know the domain and range, you can choose a window that actually shows the whole function. No guessing. When the function oscillates faster than your calculator samples, the graph can look completely wrong. A smarter window comes from the period. For sine, the period is 2 pi. For sine of 50x, it shrinks by a factor of 50. Sometimes the global window hides the interesting local behavior. Two windows can show two different truths. A classic trap, a vertical phantom line. It's not real behavior. It's your device connecting sampled points. Change scale or use dots. Some calculators compute cube roots using logs, and that can literally erase half the graph. The fix is to rewrite it in a real domain-safe form. When a device breaks a function, rewrite the expression. Same math, safer computation, correct graph. Families are your best friend. Slide a parameter and watch how the graph changes. That's how you build intuition fast. Graphing isn't just pictures. Intersections solve equations.
Where two curves cross, their outputs match. Your calculator doesn't see a curve. It samples points, then connects them. If the sampling is too coarse, the picture lies. Before you trust any graph, check the window, zoom in and out, confirm domain and range, try dot mode, and rewrite the function if needed. Challenge time. If this graph looks weird, what do you change first? The window, the scale, or the formula? Here's the classic paper fold thought experiment. Every fold doubles the thickness, so the growth is exponential. Watch how the bar explodes upward as the fold count climbs. That doubling effect is why exponentials get scary fast. The variable lives in the exponent. Compare y equals x to the a versus y equals a to the x. Same symbols, totally different behavior. Now watch the base a control the behavior. If a is between 0 and 1, the curve decays towards 0. If a is bigger than 1, it grows fast either way. Outputs stay positive. Decay is basically growth flipped left to right, starting from 2 to the x. Changing the base to 1/2 turns it into a decreasing curve. Same shape, different direction. Exponentials transform like any other graph. Reflect over the x-axis to make everything negative, then shift up to move the whole curve. Same rules as the function transformations chapter, just a new shape. The exponent rules still hold, even when exponents are real numbers. Add exponents when you multiply, subtract when you divide, and multiply exponents for a power of a power. These rules are the engine behind simplifying exponential expressions. A key comparison: exponentials versus powers. At first, a power like x squared can look competitive, but zoom out, and the exponential eventually dominates. By a lot. Here's a gut check for speed. The function e to the x hits 1 million surprisingly early. On this graph, the million level happens around x equals 13.8. That's exponential growth in action. So why is the base e special? Because the slope at the point 0, 1 becomes exactly 1. As you change the base, the tangent slope changes, and e is the sweet spot. This is the natural exponential function, e to the x. At 0, the value is 1, and the tangent slope is also 1. That clean derivative property is what makes e show up everywhere. Finally, modeling. We can take data points and fit an exponential regression curve. Once you have a formula, you can estimate growth and make predictions. The important idea: constant percent change creates exponential models. Exponentials model both growth and decay. If the base is bigger than 1, the curve rises. If the base is between 0 and 1, it falls. Same idea, constant percent change, just different direction. Quick challenge: which of these graphs represents constant percent change? Linear is constant difference. Polynomial is changing rate. Exponential is the one with constant ratio. Pick the exponential.
What if we swap the question and the answer? Instead of inputting time and getting a value, we ask, given the value, what time produced it? That's the inverse viewpoint. Roadmap: inverse functions, 1-to-1, and then logarithms as inverse exponentials. In plain English, inverse means the output becomes the new input. We reverse the arrow. Undoing can fail if two different inputs produce the same output. Then you don't know which one to pick. So we require 1-to-1, never the same output twice. That's what makes an inverse possible. Horizontal line test: if a horizontal line hits the graph twice, it's not 1-to-1. To build an inverse rule, write y equals f of x, swap x and y, then solve for y. Example: cube then add 2. To undo, subtract 2, then cube root. Exponentials pass the horizontal line test, so they have inverses. Those inverses are logarithms. Definition: log base a of x equals y means a to the y equals x. Log graphs only exist for x greater than 0, and they pass through the point 1, 0. Logs turn multiplication into addition, division into subtraction, and powers into multipliers. Change of base lets you convert any logarithm using natural logs. Base e is special. Its inverse function is the natural log, lane of x. To solve a to the x equals b, take a log base a. That's the inverse move. Recap. Inverse means undo, 1 to 1 is required, and logs are inverses of exponentials.